yeah. Oh, hot. Need some convection to cool things down.
So as bioengineers, we have a moral obligation to make sure that our chips are properly cooled. So with that in mind, we're going to talk about surface convection today. And this is, of course, one of the terms that we had in conservation of energy, which we covered in a previous lecture. So what do I mean by surface convection? I mean heat crossing through the surface of our control volume. But it's the heat crossing through the surface of our control volume, not any fluid passing through. So what do I mean? I basically mean that, let's say I have some solid, some solid chunk of material, could be a nacho chip, something else. I have some control volume that I have defined around this, and then I have some heat that passes from the solid to the fluid, like this. And I would call this maybe a Q dot sub S convection. So this is what I'm talking about, heat that passes from a solid to a fluid, crossing through the surface of our control volume in the process. But our controlled volume surface is defined in such a way where it's not, even though there might be fluid kind of zipping around this solid chunk of material here, the fluid itself isn't crossing the surface of the control volume. It's just the heat that does so, and then the fluid carries that heat away. So this is what we're talking about with surface convection. And of course, we could contrast that. We contrasted that to problems that we solved last time, where, for example, we had fluid that was actually passing in and passing out, right? So this is not what we're talking about today. We're talking about this phenomenon today. So this is what we mean by surface convection. So when we're talking about surface convection, we're going to do so, we're going to break this down, our discussion of surface convection, into a couple of topics. So first, well, understanding this process qualitatively is nice. We're engineers and we like to put equations to things. So the main equation that we'll use for modeling surface convection is Newton's law of cooling. And if you want to make puns about it, you can call it Newton's coleslaw. And it turns out one of the parameters in this Newton's law of cooling is this parameter H, which we call the convection coefficient. And it turns out that there are actually a lot of factors that go into H. So we'll just sort of talk about qualitatively factors that affect it. So we'll talk about factors that affect H. We'll then talk about typical ranges. For H in different conditions. For example, let's say we had air flowing around this material versus water flowing around it. Those two different fluids are going to be able to take away heat at very different rates from this solid surface, right? So we'll talk about a couple of different conditions and basically how H varies in that. And H is sort of this surrogate or this parameter that kind of controls how fast heat goes away from it. So we'll say, hey, what might be different H's under different conditions, just so we can sort of see, what orders of magnitude are we talking about. Then we'll do an example problem. That involves Newton's law of cooling and H. And the problem we're going to solve is we want to limit a heater power so its surface doesn't overheat. And that'll, and this will kind of bring together some of the concepts that we'll introduce here. Then it turns out that you can actually frame convection in terms of a thermal resistance. So in a previous lecture, we talked about thermal resistances for conduction. We basically said, hey, if I have a slab of material and a hot side and a cold side, there's some resistance to the heat flow that, the heat flow is proportional to some temperature difference, and the slab of material provides some resistance to that heat flow. Well, it turns out that convection can also be framed as a thermal resistance problem. So we'll talk a little bit about how do I formulate thermal resistance for convection, and then we'll do an example problem for that as well. And the example problem that we're going to talk about is how much warmer you can feel if you put on your coat in the winter. Putting on a coat to keep yourself warm, i.e. to limit the heat flow from your body to some cold air flowing around you. So this is the plan for today. Let's get started with talking about Newton's law of cooling. So, Newton's law of cooling. So let's think about this. Let's think about some solid surface right here. And the surface is hot. And then, I have some fluid out here. And let's say the fluid is cold. And the fluid is kind of, flowing past the solid surface in some way. If the surface is hot and the fluid is cold, then heat is going to flow from the hot surface into the fluid, and then that heat is going to get carried away by the fluid. And surface convection is always defined as from the solid to the fluid. So this is always defined And of course, we could have a case where we have hot fluid in a cold surface. We would still define the direction to be outwards. It's just its value would be negative, right? So, can be negative if fluid is warmer than solid. Right? So it's always defined to be from the solid to the fluid, and it would be positive if the solid is hotter than the fluid, but its value would be negative if the fluid is hotter than the solid. So we can think about things this way. We call it Q dot sub S, conv for convection, S, and that it's a surface. It's a surface convection, to contrast it from the sort of fluid actually entering into and passing out of the control volume. So Newton's law of cooling has a model for this that tries to predict the heat flow from the surface to the fluid as a function of some parameters of the system. And yet it's the same Newton, the same F equals ma Newton. He also had his hands in heat transfer as well. And this his law of cooling basically says, hey, this heat flow, which has units of watts, this heat flow is going to be proportional to a couple of things. So take a moment now, pause and ponder, what might you think this surface heat flow depends on? What parameters, what properties of the system, might this heat flow depend on? Well, hopefully you've had a chance to pause and ponder. Well, the the biggest thing that this surface, that the heat flow seems to depend on, is how hot the hot surface is and how cold the fluid is. Right? So, if I want to cool something down quickly, I'm not going to pour lukewarm water over it. I'm going to pour ice cold water of it. So this heat flow from the surface to the fluid is proportional to the temperature difference between those two things. Right? So, but I have my fluid that's cold out here. This fluid, the whole fluid, is actually at a non-uniform temperature, right? So, I have some fluid out here. I might call the fluid way out here that hasn't yet encountered the surface. I might call this fluid out here, I might say that this is at, let's call it T infinity, to basically indicate that it's fluid that's far away from the surface. And I might say the surface right here has some temperature Ts. So surface temperature is Ts. The fluid temperature far away from the surface is at T infinity, but of course the fluid that is closer to the surface might not necessarily be at that temperature right here. But we're at this point in our development, we're looking for a relatively simple model. We're just trying to get the basics down. So we're not going to consider the details of how exactly the temperature varies between Ts and T infinity. We're just going to say, hey, some fluid far away is at T infinity, the surface is at Ts, and we know that the fluid temperature varies between them. But this heat flow is going to be proportional to the difference between Ts and T infinity. So Ts minus T infinity. And we can see that if Ts is greater than T infinity, then we're going to have something positive. If Ts is less than T infinity, then we're going to have something negative. But baby you-know-who would, of course, be very upset about this, because temperature difference is going to have units of Kelvin, and we have watts over here on the left-hand side. So we're going to need some other stuff on the side here. So what else? What else might this convection depend on? Well, it's also going to depend on the surface area of the solid that is in contact with the fluid, right? So there might be some surface area. That's in contact with the fluid, and we know the more surface area there exists around, the more surface area exists on something, the more readily that that heat can get convected away from it. So, for example, when my toddler has food that's too hot, she asks me to cut it up into little pieces so it will cool down faster so she can eat it. So when I cut up the food into little pieces, I'm increasing the surface area of that food, so I'm increasing the convection, the heat flow due to convection away from it. So convection is proportional to temperature difference. It's also proportional to the surface area. And if you increase something's surface area, then you're going to essentially allow more path for that heat to get convected away to the fluid. Surface area would, of course, have units of meters squared. And, when you were thinking about, hey, what could this depend on? You might imagine, hey, it could depend on what type of fluid I have. What is the fluid's specific heat? What is the fluid's density? What is the fluid's viscosity? Is the flow laminar or turbulent around it? You could say, hey, this there's a lot of things that this heat flow could depend on. But oftentimes what we do is, sometimes it's really hard to predict exactly how all of those factors play into it. But so a lot of times what we do is, for the sake of simplicity, we just say, hey, these are the two things that heat flow is going to be most proportional to, and everything else, we just lump it all together in this one other term called H. So H is what we call the convection coefficient, and it's sort of a catch-all for the properties of fluids, for fluid properties, flow conditions. Right? Am I letting the nacho chips just let their heat off to the environment, or am I blowing on them to cool faster? H would sort of account for whether I'm blowing or whether I'm just letting them chill. Right? So fluid properties, flow conditions, maybe some of the geometry. something like that, right? So H is sort of this catch-all. So what units does H have? We typically think of H as having watts per meter squared Kelvin to get both sides of this equation to line up unit-wise. So this is what we call Newton's law of cooling. The heat flow is proportional to the temperature difference, i.e. the greater the difference between the fluid and the surface, the more heat's going to flow, the faster the rate of heat of joules leaving that surface. Also, the more area there is in contact between the fluid and the surface, the more joules can leave it in a given amount of time. And then sort of everything else, properties of the flow, properties of the fluid, all of that stuff is lumped into H. One thing that H doesn't depend on, H actually does not depend on H basically doesn't depend on the solid materials at all. Basically, everything to do, basically as long as the surface temperature is prescribed at Ts, it doesn't matter what's happening underneath. What's happening underneath doesn't matter at all so long as the surface temperature is whatever surface temperature it is. H is almost entirely governed, or H is basically entirely governed by what's happening in the fluid, right? So as long as the solid is maintaining the surface at Ts, it doesn't matter whether the solid is, brick or copper or skin, right? It could be anything. It's only really the properties of the fluid and the flow of that fluid that affect H. So that's a key distinction to make here. So Newton's law of cooling, there it is. So this Newton's law of cooling has this H in it, and this H is what we call the convection coefficient. Let's now talk about what factors might affect H. So when I think about what factors might affect H, I might want to sort of break it up into a couple questions that I ask myself in terms of what might H depend on. So the first thing we might think of it is, what drives the flow? And there can sort of be two scenarios for what's driving the fluid flow. One scenario is what we call forced convection, which is basically me blowing air, actively blowing air on the nacho chips. Right, so this is, we blow fluid across the solid surface. The alternative is what we call free convection, which is the flow is created due to the buoyancy of the fluid. So we all know, everyone's told you, oh, hot air rises. Well, basically, hot air rises, and the rising of the hot air pulls heat away from the surface, and then cold air gets brought in to then get heated up. And basically, it's the buoyancy of the flow that the buoyancy of the heated fluid or that drives the flow. So buoyancy drives the flow. And you can imagine, forced convection usually is more effective at cooling things quickly than free convection. So this, if we're sort of considering, we might get very different H's depending on whether we have forced or free convection. Another factor that affects H is the geometry of the surface. So here I said, it doesn't depend on the solid materials, but it does depend, but the flow, so H doesn't depend on what materials the surface is made out of, but the shape of the surface matters a lot, right? So we can talk about convection internally in pipes. So for example, let's say I had a pipe, and the pipe had a hot surface right here, and then I was pumping cold fluid into that that hot pipe to warm the fluid up as it goes, I can have convection essentially from the interior of the pipe into the fluid. I could also, for example, have external. I could have an external flow where, for example, let's say I have a flat plate, and then I have some flow flowing past that flat plate, and I want to, predict how heat is being transferred, let's say, from the plate to the fluid. You can basically imagine, these are sort of two very different types of flow, and basically the geometry of the surface might affect what H might appear for internal flows in a pipe versus external flows over a surface. H also depends on, sort of what's going on in the fluid. And we can imagine, one of the most important factors in terms of how this fluid can carry away heat from the solid is whether the flow is laminar or turbulent. So what goes on here? Well, there's basically, if I picture fluid flowing past something, there's usually kind of a boundary layer, but where the flow sort of transitions between zero flow right at the surface up to whatever the fluid is doing externally far away. So there's this boundary layer, and it turns out that this boundary layer, we get very different H's about whether your boundary layer is laminar or turbulent. You get very different. And you can imagine turbulent flows usually result in higher H. So why might turbulent flows result in a higher H? Well, pause and ponder and think about that. Why might turbulent flows result in a higher H? Well, it turns out that turbulent flows, what characterizes turbulence? Turbulence is all this sort of like, so let's say I have some solid right here. Turbulence is all this kind of swirling, chaotic eddying, and what takes the heat away is cold fluid encountering the surface and then leaving once it's picked up some heat. And laminar flow, basically all of those streamlines just kind of all keep to themselves, and it requires that heat to sort of cross streamlines to get carried away. Whereas turbulent flows, mixing everything up, it's swirling, it's getting that cold fluid right in contact with the surface and then sweeping it away. Sweeping that now hot fluid away to get far away from the surface to replenish with more cold fluid. So turbulent flows typically result in higher heat transfer coefficients, higher convection coefficients. And then finally, the last thing that H depends on is what are the properties of the fluid? So take a moment now, pause and ponder. Which properties of the fluid might be important, might factor into H? Well, have you had a chance to pause and ponder? Well, we said whether the flow is laminar or turbulent has an effect on this heat transfer coefficient, right? So the properties of the fluid that factor into whether it's laminar or turbulent would also affect, would also sort of indirectly affect H through this laminar or turbulent phenomenon, right? So what fluid properties govern whether the flow is laminar or turbulent? Well, the viscosity and the density do. But of course, also some thermal properties of the fluid are going to be important as well. So even though we're talking about surface convection here, and we're not talking about this scenario where we have flow entering the control volume and then leaving, it turns out the specific heat of fluid, even though the specific heat of fluid was very important for this phenomenon, specific heat of the fluid also affects the fluid's ability to convect away in a surface fashion. So the specific heat of fluid, the specific heat capacity turns out to be very important as well. And it actually also, another property of the fluid that we haven't really talked about yet is fluids have thermal conductivity as well. Right, so we talked about thermal conductivity for solids. Fluids also have thermal conductivities, and it turns out that like mercury is actually a really great material used to convect away heat, because mercury actually has a very high thermal conductivity. I mean, it's problematic in terms of safety and all that stuff, but you can actually get really great convection coefficients if your fluid has really high thermal conductivity. So these are the four main fluid properties that affect H. There can be a few more if you talk about free convection, and there can be a few more if the fluid encounters a surface and, like, let's say boils because it gets so hot. Then you sort of need to consider a few others. So we'll say these four properties are the most important in determining H, plus potentially others. But we mostly won't talk about them in the context of this class. So, H kind of depends on a lot of stuff, and there's a lot of problem-specific factors that go into an H. So, what are we going to do? How are we going to approach H in this course? Well, for the next couple of lectures, we're basically going to have the clouds open up and Professor Lannin's face poke through and says, H is such and such watts per meter squared Kelvin, and then the clouds will close back up, and then you'll just sort of take H as something given. But towards the end of this course, in the last couple of lectures, we're going to be able to, for certain types of flows, particularly flow in pipes and flow over flat plates, we're actually going to be able to find your own H. So we're not going to rely on being sort of given an H. We're going to say, hey, if we knew these properties of the fluid and some properties of the flow, we're actually going to be able to predict our own H to then be able to predict, things like heat transfer and stuff like that. So that's where we're headed. For a while, we'll just be given H, but then I'm going to provide a structure whereby you can calculate your own H given conditions of the flow. So what's up next? Well, we talked about some factors that affect our convection coefficient. Now let's talk about some typical ranges that you might get for H under different conditions. So let's build ourselves a little chart. Of what flow condition and then what we might get for H, in where H would have units of watts per meter squared Kelvin. So kind of going back to these questions, free versus forced, or forced versus free convection, and also kind of thinking about properties of the fluid. It turns out that gases and liquids are basically radically different from one another. I mean, I don't need to tell you this, but spoiler alert, gases and liquids are different from one another. Well, it turns out that the range of H's that you get for gases and liquids are pretty different from one another, and that range of H's that you get for forced and free convection tend to be pretty different from one another. So what might we talk about? Well, you could have free convection of a gas, or free convection of a liquid. Both gases and liquids are fluids. Or you could have forced convection, and that could be either of a gas or a liquid. And so free convection for a gas, of course it depends on exactly what gas you're talking about, and exactly how the flow is happening around it. But typical ranges you might see for H for gases might be something like 3 to 25 watts per meter squared Kelvin. We can contrast this to liquids. Liquids are generally much better at taking away heat from surfaces than gas. So liquids typically have a range of 20 to 1,000 in terms of their H's, right? So we can get multiple orders of magnitude higher if we go to liquid cooling versus gas cooling. And then if we think about forced convection, we could have forced convection of a gas, i.e. I could blow on my nacho chips with gas, or I could take those nacho chips and I could put them under the cold tap and flow a bunch of liquid on it. Of course, culinarily that would be a bad choice, but in terms of heat transfer, that might be a more rapid way to cool down my stuff. So forced convection of a gas, might typically be on the order of 10 to, let's say, 500 watts per meter squared Kelvin, whereas forced convection of liquids can typically range from 100 to 15,000 watts per meter squared Kelvin. So, what's the key takeaway here? Free convection for gases can be pretty wimpy. Forced convection for liquids can be pretty robust in terms of, pretty rapid in terms of heat transfer coefficients. Generally, liquids are better than gases, and forced is better than free in terms of having high H's. One final thing that I want to talk about is there could be a phase change. So you've all seen in the movies the blacksmith very dramatically is pounding on that iron sword that's red hot, and then they take the sword and then they plunge it into a bath of water, and steam erupts from the sword. It's very dramatic. They've quenched the sword. It actually turns out to increase the material properties of the sword. But this phase change, for example, where the fluid in contact with the solid goes from a liquid to a gas, that phase change actually gobbles up a ton of energy in the process. So phase change, convection due to a phase change where we go from a liquid to a gas, can actually be even better than some of these, something maybe in the range of 5,000 all the way to 100,000 watts per meter squared Kelvin. So what's the key thing? If you want to cool something down quickly, basically pour water on it where the water boils away. And you can get very, very high heat transfer coefficients from that. But as bioengineers, that might not always be the scenario. As bioengineers, you might be typically dealing with these conditions. So where does that leave us? I'd say between typical ranges for H, we now are going to approach an example problem where we're trying to relate temperatures and heat flows and things like that. So let's proceed with that. So let's proceed with this example problem. So oftentimes we might have a scenario where we have some cylindrical heater, and that cylindrical heater is immersed in a fluid, right? So let's say I have a heater that looks like this, and oftentimes, this might be used in like a bioreactor to the heater sort of sticks into the fluid, and then the fluid is kind of flown past the heater like this, and the heater has some embedded electric resistive elements in it that you flow electricity in, and then it comes out as heat. That heat eventually gets convected away to the fluid. So let's say the fluid comes in at some temperature T infinity, and we know, let's say, like the length and the diameter of the cylinder. And let's say, this is a scenario where the clouds have opened up and Professor Lannin's face came through and told you what H was in this situation as well. So let's say, we have this water flowing by the heater, and let's say, we want this heater to, provide as much heat as we can to the fluid, but not so much that the fluid immediately adjacent to the heater boils. So we want as much heat as possible without boiling the fluid at the heater surface. And you can imagine, there might be similar problems, maybe not necessarily with the boiling fluid at the heater surface, but if you were flowing, let's say, media past a heater in a bioreactor, there are certain temperatures at which you ruin some of the growth factors or other components of the media. So, it might not be boiling in certain cases, but maybe it might be, just some unacceptable temperature where you damage the reagents or the cells or things like that. So a lot of times we might want as much heat as possible, but not so much heat that the fluid right at the surface gets too hot. So let's put some actual numbers to this. Let's say this fluid, the fluid comes in past the heat, comes into the heating system at 20 degrees C. Let's say the length of this heater is 20 centimeters. Let's say the H is 1,000 watts per meter squared Kelvin. The diameter is 1 centimeter. And we want to know as much heat as possible. We basically want to know what heat, essentially how many watts we can have this electric heating element produce without having the fluid, having the water boil at the surface, without boiling the fluid, which is water, at the surface. And in particular, we're looking for this scenario when the system is at steady state. So we have an ample supply of 20-degree water coming in, and we're basically flowing that water past it and heating up, and our system is kind of at steady state here. So we're basically saying, okay, if this system is at steady state, I'm constantly having fresh 20-degree water come in. Basically, how much heat can this heater dump into our system without the water molecules immediately adjacent to the surface here getting hotter than 100 degrees C. So we have some system like this. What might we do? Well, spoiler alert, we're going to, this is going to be a convection related problem. What does convection help us do? Convection helps us relate things like heat flows to things like differences between surface temperatures and T infinities. Right? So our problem-solving strategy is going to center around convection, which basically gives us a relationship between T surface, T infinity, H, the surface area, and Ts T infinity, H, the surface area, and the heater power. So convection will kind of give us a relationship between all these. Strictly speaking, it's not convection alone, but convection as a part of conservation of energy. So we're going to apply conservation of energy to this system here. Convection will be one of the terms in there, and that's going to relate a lot of these known given parameters to this unknown parameter up here. So this is going to be our problem-solving strategy. So we could go back in the notes and we could put that full version of conservation of energy with all of the possible terms in it, but I'm just going to start with the abbreviated form of conservation of energy. So with the abbreviated form of a conservation of energy, it's the rate of accumulation is equal to the rate in minus the rate out plus the rate of generation. And of course, if I'm applying conservation of energy, I need to define my control volume. So what am I going to do for my control volume? Well, if I'm anticipating, H and relationships between surfaces and T infinity, I'm probably going to want to define my control volume in such a way that my surface of the control volume is coincident with the solid-liquid interface, so I can employ surface convection. Right? So surface convection is going to be this key relationship here. So I want to make my control volume surface coincident with the solid-liquid interface such that I can apply convection at that surface. So what is it going to look like? My control volume is basically just going to be just barely outside of the solid surface right here. So that's going to be my control volume. So I can apply conservation of energy to this control volume that I sketched out here. So let's think about various terms that we might be able to get rid of or not. Rate of accumulation. Well, I said my system's operating in steady state, so I can get rid of my accumulation term because I'm steady. Then, so what other terms might appear in His? Well, when we talked about generation terms, sort of being like that volumetric heat generation that often occurs with like chemical reactions or electrical heaters. So I'm going to take my Q heater and kind of put that in my rate of generation term, right? So my rate of generation is going to be Q heater. So, and then if I'm going to sort of look at like a simplified version of my control volume right here. So I basically have Q heater generating heat inside of this control volume. And then I also have my Q convection, my Q dot surface convection going from the solid to the liquid out of this surface, right? So I don't have any rate of accumulation because my system is steady. I don't have any ins, right? My heater is a generation. I don't have any ins, but I do have Q dot surface convection as an out. And then I have Q dot heater. So basically, what's going on here? I have no accumulation, no ins. My rate out is this convection, and my rate of generation is what's going on inside the control volume, which is Q dot from the heater. So, we probably could have just intuited this result, but it's useful to sort of follow the formalism that we have here. So what can I do? Well, this Q dot surface convection, I can apply Newton's Cole's law, or Newton's law of cooling, to here. So what might that look like? Well, Newton's law of cooling says that it's Ts minus T infinity, which is a given, times the surface area times H is my convection. And if we brought this over to one side, this is going to be equal to the Q dot of the heater. All right, so we have two terms which we might be able to work out here, perhaps in terms of these givens. Right? So I can work out the surface area, and I can work out Ts. Right, so what's Ts going to be? Well, if I want as much heat as possible without boiling the fluid immediately adjacent to the heater, boiling the water immediately adjacent to a heater, I basically want to ramp up Q heater until Ts is equal to 100 degrees C. Because once that surface temperature gets above 100 degrees C, then I'm going to start boiling that fluid. So I can basically set Ts to be just barely at the boiling point of water, so the water doesn't actually boil when it gets there. Right, so what does this mean? I can basically treat Ts now as a known, basically right at the boiling point of water. Surface area, if this heating element is cylindrical, right, it has some diameter d and some length here. If I neglect the tips, right, if I neglect what's going on, if I neglect the area of the tips right here, right here and right here, most of the area of this cylinder is going to sort of be that unwrapped rectangle. The surface area in that case would basically be or basically be pi times d times L, where pi d is essentially unwrapping this, the circumference of this circle. Pi d would be that dimension, and then L would be the other dimension. So that's the surface area right here. So what does it mean? This basically means I have Q heater entirely in terms of knowns. So what's that? It's like Ts minus T infinity times pi d L times H. So I can plug in all of these knowns constant. So what might that look like? It might look like 100 minus 20 And this temperature difference, I mean, it's degrees C here, but the difference, I guess I could express in, a difference in degrees C is the same as a difference in Kelvin, times pi d is 1 centimeter, which would be 0.01 meters. L is 20 centimeters, which would be 0.2 meters. And H is 1,000 watts per meter Kelvin. Sorry, 1,000 watts per meter squared Kelvin. We look at the units. Meters, cancel with the meter squared here. Kelvin cancels with this, and I end up with just watts. And I crunch the numbers, and I end up with 502 watts, or half a kilowatt. And just to sort of put this in perspective, that's about half the power that your microwave has when it's on full blast. Or it's about the power of like a reasonably beefy desktop PC, something like that. So that's what we have here. So what did we do? We basically we applied conservation of energy. We did some inferences about what's accumulation, ins, outs, and generation, and then we put in the particular out surface convection. We formulated that in terms of Newton's law of cooling. We plugged in some knowns. We formulated everything in terms of knowns, and then we were able to get our heater power entirely in terms of knowns. So that's the problem-solving strategy. So what's up next? Well, we just completed this example problem where we could essentially relate temperatures and heat flows from for a system where heat was going from a solid to a surrounding liquid, and we did that with conservation of energy and Newton's law of cooling. Next up, let's talk about thermal resistances for convection. So in previous lectures, we said, in general, a thermal resistance is kind of defined as how much thermal resistance is essentially defined as a sort of delta T divided by a Q dot, right? So, last time we basically said, hey, this delta T could be, for example, the temperature difference on two sides of a wall, and the heat flow could be a heat flow through the wall. So this, we could say this is, for conduction through a slab. We also can formulate this in terms of convection. And convection as well. So what I'm gonna say to you is formulate, get an expression for what the thermal resistance due to convection is, as a pause and ponder question. So what is the thermal resistance due to convection? Well, we can take it back. So hopefully you've had a chance to think about it. We can take it back in terms of Newton's law of cooling. Q dot surface convection is equal to H times AS times TS minus T infinity. So if I use this as my delta T, and I use this as my Q dot, well, I can just, take Q dot over to this side. I can take H times AS and bring it over to this side. And what might that look like? The thermal resistance for convection is 1 over H times surface area. So what does this mean? If H is higher, then there's less of a thermal resistance, right? So if I have some surface and heat's flowing out of that surface due to convection in the environment, the bigger H is, the less resistance there is for heat to flow out of this surface and into the fluid. Similarly, the more surface area there is, a large surface area is going to have plenty of area for heat to convect off to the environment, plenty of contact between the surface and the fluid, so there's going to be a low resistance, right? So the higher the surface area, the lower resistance. And this is why, for example, if you're, out in the cold, you might sort of bring your arms in, hunch yourself up, right? If you're cold at night, you might curl up into the fetal position to try to limit your overall surface area, so your body heat, so your body is rejecting less heat to the environment, right? You can conserve the heat by increasing your thermal resistance due to convection by trying to lower your surface area. That's why you huddle up when it's cold. So this is thermal resistances. We can combine thermal resistances in series So, so one example might be, let's say I had a slab of one material, and then I paired that with, a slab, like a slab of some different material. So, let's say this is one material, let's say this is another material. I could formulate a thermal resistance for, for this one. I could formulate a thermal resistance for this one. And if I wanted to consider, heat flowing from one side all the way through both materials to the other side, I can basically say, hey, there's some heat that flows, that has to, it flows through one and then has to flow through the other to get through. I can basically say, hey, there's some equivalent resistance to these. If the heat flows through one and then through the next, they're in series. So the equivalent resistance is equal to the sum. Similar to how you would have electrical resistances or fluidic resistors. If I have a fluidic resistor where I have one pipe and then I connect a second pipe to that, the equivalent resistance is basically going to be the sum of those two resistances. And it's the same with solids as well. I can also, this isn't just combining solids in series. I can, for example, have some conduction as well as convection, right? So let's say I have to have heat that flows, that is first conducted through a surface and then convected from the surface to fluid all the way out here at T infinity. Right, so I could have a conduction and then a convection, and I might say that, if I want to relate the temperature here to T infinity all the way out here, then these two would be in series. So I can have multiple conductions in series. I can also have a conduction and then a convection in series. And if you might have heard of like energy saving windows in your house. Well, the energy saving windows in your house basically have multiple panes of glass where there's like air, glass, some inert gas, glass. Some of them actually have 3 layers of glass. And basically what happens is you have to have a thermal resistance due to convection to go from the ambient air in your room to this surface, resistance due to conduction, resistance due to convection, another resistance due to convection on this side, conduction, convection, convection, conduction, convection, and then we're outside. So having multiple panes of glass not just adds the thermal resistance of the glass, but also needing to convect between the gas and the surface, right? So if you want to save on your energy bills and also save the earth as well, having multi-paned multi-planed glass essentially stacks up a whole ton of thermal resistances, some of them from conduction and some of them to convection, to really get a very beefy equivalent resistance, so you don't lose too much heat to the environment. So qualitatively, this is what's going on. We can have thermal resistances due to convection, and we can dust off our notes from last time to have thermal resistances for conduction. Let's do an example problem where we sort of use some of those to make inferences about temperatures and heat transfer. So let's do this example problem, and we'll do the example problem of why it's a good idea to wear a coat in the winter. So let's look at 2 scenarios. So scenario number 1 is I'm wearing a shirt. I'm out in the winter and I'm wearing a shirt and a coat. And if I'm wearing a shirt and a coat, my body, like my muscles, all the metabolism of all my cells, all that stuff, I basically, my body produces my body produces 65 watts of heat. And that, just to put that in perspective, 65 watts is about what your laptop might use if it's just kind of chilling, well, or heating in this case, right? So if you're, so I might say this is my Q dot with a coat. So if I wear a coat, my body produces 65 watts, watts of heat, and there it is. And let's say, I have two scenarios, and in both cases, my skin temp, so let's say T skin, in both cases, my skin temp is equal to 34 degrees C, and and let's say I want to keep warm. I want to keep warm in 0 degrees C outdoor weather, right? So the air far away from me is at 0 degrees C. So one scenario, I have a shirt and a coat, and under this condition, my body produces 65 watts of body heat. Let's look at the other scenario where I've disobeyed my mother's advice, and instead I've gone just outside with a shirt. Let's try to figure out how much body heat my body would need to produce in order to keep my skin at 34 degrees C if this were the case. So, let's say I'm outside with a shirt only. How much body heat? Basically what is my body heat with no coat in order to sustain this? So let's sort of imagine what these systems look like. Well, here I have, for the shirt and the coat, here I have my body, and my skin is right here at TS. If I have a shirt and a coat, there's first a layer of shirt that's kind of in contact with my skin, and this shirt, let's say this shirt has a thickness, we'll call it L shirt. The thickness of the shirt is, let's say it's about 1 millimeter. And then in addition to wearing a shirt, I'm also wearing a coat, a nice big thick coat. I'm a New Englander after all. So I'm wearing a nice big thick coat that's in contact with my shirt. And this coat, it's a pretty thick coat. Let's say it's 20 millimeters. So the thickness of that coat is 20 millimeters. And then there's this, there's the surface of my coat, and heat is convecting off of the surface of the coat. And very far away from the surface of the coat, we can say it's T infinity, right? So T air, we could also call this our T infinity in this case. So I have T infinity out here. And I'd say, hey, my body heat, I have my body surface temperature right here. That heat flows first through the shirt and then through the coat, and then via convection from the surface of the coat all the way to T infinity. And we know what heat this is. This is our 65 watts right here. So my 65 watts of body heat flows through my shirt and through the coat. Through all of those layers to do this. If I have no coat, I just have my body temperature right here. And I have this measly 1 millimeter shirt. And under this scenario, I have perhaps a lot more heat. Flowing between my TS, my skin temp in the body, all the way to T infinity over here. So if I wanted to formulate these two systems, let's assume we're in steady state. It's not like I just stepped out of the door. Let's say I'm foolish enough to have spent a long time out in the cold, either with a coat or without a coat. So let's assume we're in steady state. Let's also assume that the surface, let's take one more bit of information. Let's say the surface area of a human, of me, is about 2 meters squared. And in this case, this would both be, this AS would essentially be both the surface area that the surface of my coat is convecting, or the surface of my shirt is convecting to, but in a sense it's also the cross-sectional area that the heat is flowing through via conduction, right? So this is also, in a sense, cross-sectional areas for conduction, right? Because basically the heat first flows via conduction through my clothes and then via convection out. And essentially the cross-sectional area is the same as the surface area. The cross-sectional area for conduction is essentially the same as the surface area for convection. So let's figure things out. So what's the deal here? Well, I want to figure out how much heat my body is producing with no coat. But I'm not going to have quite all the information I need to just sort of consider the shirt-only case. I'm actually going to need to consider the shirt and coat case to help get some information to figure the shirt-only case. So where are we going with this problem? Well, if I'm thinking about heat flowing through multiple layers, first through the shirt, then through the coat, then via convection, I'm thinking this is looking a lot like resistors in series. So what might this look like? I might have a resistor for the shirt, a resistor for the coat, and then a resistor for convection. And on this one side it's Ts, and all the way over here it's T infinity. So I might call this first one R shirt. I might call the second one R coat. And I'll call this last one R convection. And then if I think of the shirt-only case, well, the shirt-only case is basically the same as this, but without this coat resistor. So it's basically just the shirt and convection providing any sort of resistance. For this scenario, I have Q dot no coat, essentially flowing through these three resistors. For the shirt-only case, I just have two resistors, one for the shirt and then one for convection between my Ts and my T infinity. So I'm leaving these resistors as things that are as of yet unknown, but we can start putting these resistances in terms of knowns, or maybe in terms of a couple of unknowns. So what might that look like? Well, our shirt, we can kind of say, hey, let's assume that my clothes act like these one-dimensional slabs. So let's assume we're in steady state, and clothes are like slabs of material. They're like walls, essentially. So we could dust off our notes, and the resistance of the shirt would be the length of the shirt divided by the cross-sectional area of a human, I guess, in this case. And oh, there are a couple of pieces of information that I should have given you. Sorry, I forgot to tell you what the properties of the shirt are. So you can look up what thermal conductivities, you can even look up thermal conductivities of like materials that make up clothes, because engineers actually engineer high performance clothes. The thermal conductivity of shirt, of cotton that would make up shirt, is about 0.04 watts per meter Kelvin. and let's say my coat is made of a real high performance material that has a lower thermal conductivity of 0.02 watts per meter Kelvin. So the K's, I was sorry, I should have given them earlier in the problem, but the K's we're supposed, we're treating those as knowns. So we have a K shirt right here. So what does this mean? I can basically treat R shirt as a known, right? I could plug in all of these numbers and get a number for R shirt. I could do the same thing for R coat. I could do the same thing for R coat as well. I can treat that as a known. Our convection is a little bit trickier. It's 1 over h times surface area. And we weren't given h in this problem, right? So, this wasn't a case where the clouds opened up and Professor Lannin's face gave us h, but we could assume that, there is some h, and we could hope that h is the same in both of these cases. Strictly speaking, it actually wouldn't be, but, to a first approximation, it would be. So let's assume that h is the same. Let's assume that it's the same h for both. So what can we do? We can hopefully use this first scenario. We'll use this to determine h, which is as of yet unknown, and then once we have h, we'll then take h and plug it into this system to figure out our as of yet unknown Q dot with no coat that's flowing through these resistors. So if I'm thinking about equivalent resistances, the equivalent resistance for this circuit is the sum of these three resistors. And the equivalent resistance for this one is just the sum of these two. My delta T for both of these would basically be 34 minus 0 degrees C. So I could basically say my delta T is going to be 34 Kelvin. So that's my delta T. So I basically have to set up a system of two equations and two unknowns. So what's that going to look like? Well, my Q dot with no coat is going to be equal to delta T, which is known, divided by L shirt, divided by AC times K shirt, plus L coat, divided by AC times K coat, plus 1 over my as of yet unknown H times AS, which is known. And where is this term in the denominator coming from? Where is this whole equation coming from? Well, we could formulate, the general form of resistors is that Q dot is equal to delta T divided by the resistance, and the resistance overall for this thing is basically the sum of the three resistances. So I have each of the three resistances right here. We formulated these up here, and the Q through the whole system is the temperature difference across the whole system, sort of replacing these three resistors with one equivalent resistor. So what does this mean? I basically have one equation with one unknown. If you plug in all of these numbers, if you plug in all of these numbers that we got here and, cancel all the units and all that stuff, you end up with H is equal to 47 watts per meter squared Kelvin. We can then take this H and we could formulate this equivalent circuit. So what's that going to look like? Well, the Q dot with, this was Q dot with a coat. My mistake. Sorry. Q dot with a coat. This is Q dot with a coat. This is this scenario right here. Sorry, Q dot with a coat was this. So we use Q dot with a coat to essentially find H, and then we plug that H into this one to give us Q dot without a coat. Q dot no coat. And that's going to be equal to delta T divided by L shirt over AC times K shirt plus 1 over, and I can now treat H as a known and my surface area right here. When I plug in the actual numbers for this, what do I get? I get 1470 watts. This is insane. This is about as much heat as an electric kettle. You know those like electric kettles that you plug it in and it like boils, you know, a pot of water in just a couple of minutes? That's the amount of heat that we're talking about, right? So what's the key thing here? Your body, you know, if you put a coat on, it only leaches about 65 watts, you know, enough like a modest laptop. Whereas if you don't wear a coat, it requires as much heat as an electric kettle to basically keep you warm. Now, does the metabolism of our body support 1470 watts? No. Our metabolism can't support this. So our metabolism can't support what's going on here. So pause and ponder. You know, if our metabolism can't support 1470 watts, you know, what happens if we go outside? What happens if we go inside and, you know, our metabolism can't support the 1470 watts in order to sustain this heat transfer? Well, what happens, you know, we said we were assuming here that our surface temperature, you know, that our body decides to keep our skin, even if we're wearing no coat, our body decides to keep our skin at a balmy 34 degrees C. And it turns out that, you know, because our body recognizes that it doesn't have the metabolism to support this 1470 watts just dumping out of our skin, our body lowers, because it can't support this, our body lowers our skin temperature. And how does our body lower our skin temperature? Well, our skin is full of little capillaries, and those capillaries, you know, do things like carry oxygen and metabolites, you know, to and from our cells, but it also carries heat to the outer layers of our skin. But if our body's like, hey, we're losing too much body heat, we won't be able to sustain this, our body closes off all of the capillaries to your skin. So it lowers skin temp by closing capillaries. So it basically closes off the capillaries, saying, hey, we're losing too much heat, I'm not going to flow blood to the skin. This, by closing off the capillaries, that basically lowers the skin temperature, and by lowering the skin temperature, then we lower the delta T that's going to drive this heat flow. Well, what's problematic about closing the capillaries? If you do this for long enough, it kills your skin tissue, and you get frostbite. So if you do this for too long, you get frostbite, which is in part due to starvation of your skin from the stuff that blood provides, but also part just due to the damage that cold has to your cells. Well, there's a bit of a public safety announcement that I'd like to make here. When you drink, if you've consumed a lot of alcohol, alcohol is a vasodilator. And what is a vasodilator? A vasodilator is basically something that prevents the capillaries from restricting. So, you know, some people might have said, "Oh, have a drink; it'll keep you nice and warm." Yeah, you'll feel warm. You'll feel warm because your body won't be cutting off those capillaries. But what's potentially problematic about that, so it's a vasodilator, your body feels warm because it doesn't cut off capillaries. But what's potentially problematic about that, that means your body's basically going to be keeping up producing this 1470 watts. So your body feels warm because it doesn't cut off your capillaries, but it's actually dumping heat. And what might happen is it might actually lower your core temperature. So rather than just cutting off the flow to your capillaries and your skin being a little unhappy because it's cold if you're sober, if you're drunk, the alcohol is a vasodilator, you feel warm, but your core temperature is plummeting and you get hypothermia. So unfortunately, people die. People die all the time from going out drinking, not really paying attention too much and, leaving their coat somewhere, but them feeling warm because their capillaries aren't closed, but their core temperature plummets, and if they pass out somewhere outside in the winter, they die of hypothermia. So what do you need to do? If you go out drinking, make sure you do so with other people that you're comfortable with, and that you wear a coat if you do so in the winter, and take a cab home rather than walk, or take an Uber, I guess, or a Lyft. So that's the story. Public safety announcement. So what is this? We can do heat transfer to help save lives. So hopefully you've enjoyed this lecture. Thanks for your attention, and good luck with your study of heat transfer. Take care.